Throughout the next couple chapters, the book is going to use molecular orbital theory to explain a lot of the properties of conjugated and aromatic systems. Conjugated and aromatic systems involve delocalized electrons, and molecular orbital theory is particularly good at explaining delocalized electrons, where some of our other simpler theories of chemical bonding, like Lewis structures and valence bond theory, really kind of break down. Now, we don't cover molecular orbital theory much in general chemistry, and so I thought it would be a good time to sort of give an introduction to molecular orbital theory. So one of the things you would have talked about in general chemistry is the wave-particle duality of nature. And part of that is the idea that matter can behave not only as particles, but it can also behave like waves. And this was a fairly revolutionary idea when it was proposed in the early 20th century, and it's what largely led to the development of quantum mechanics. Now, we don't see the wave-like nature of matter in our everyday lives because the things that we're used to dealing with are too big. We generally only see the wave-like properties when the matter becomes very small, on the order of atoms and, even more importantly, electrons. So the smaller the mass, the more pronounced the wave properties will be. So for something very tiny like electrons, it turns out it's really important to consider their wave-like properties. And so the mathematical equation that we have that explains the wave-like properties of molecules and atoms and electrons is the Schrödinger equation. Now, we're not going to go through any of the math in solving the Schrödinger equation, but we're going to talk about some of the qualitative repercussions and how that applies to molecular orbital theory and chemical bonding. And you're already familiar with some of the consequences of the Schrödinger equation. The orbitals that we've been talking about throughout general chemistry and organic chemistry, these come from solving the Schrödinger equation. And these orbitals tell us about the regions of space where we're likely to find electrons in an atom. So quantum mechanics deals a lot in probabilities. It turns out we can't know exactly where an electron is in an atom. We can only think in terms of probabilities. Where are we most likely to find an atom? And so the orbitals tell us about the regions of space where we're most likely to find the atoms, right? So a 1s orbital has a spherical probability density, right? There's a spherical region of space where we're most likely to find the electron. The highest probability at the nucleus, and then the probability drops off as we get further away from the nucleus. So in the Schrödinger equation, we're treating the electrons as if they behave like waves. A really important property of waves for our discussion is interference. So if we imagine two waves that have the same frequency, if we line them up so that what they're called in phase, right? So the peak of one wave matches the peak of another wave, and the valley of one wave matches the valley in another wave, we would say these waves are in phase. And when we combine waves that are in phase, we get constructive interference, right? Those waves combine to make a new wave that has a higher amplitude than the two waves that we started with. Alternatively, if we were to combine these waves when they're out of phase, right? So where there's a peak in one wave, there's a valley in the other, and vice versa, we're going to get destructive interference, where these waves are going to cancel each other out. And if we're thinking about light waves, we'll get sort of a dark spot. When waves are out of phase, they destructively interfere, and essentially they cancel each other out. So the wave function that, for example, describes an electron's properties has a lot of similarities to other waves that we're familiar with, similar to, waves in a lake, right? If we imagine this is the average level of a wave in a lake, right? When the wave function has a value higher than that, we would say that it has a positive phase. When the value of the wave function is less than that average value, we would say that it has a negative phase. And where the value of the wave function is 0, we call that a node. Now note that the phase has nothing to do with charges. It's just telling us about the amplitude of the wave in that region. So the orbitals that we're familiar with are generated mathematically from wave functions. And so the phase of the orbitals can be different in different regions of the orbital. The phase can either be positive or negative, or in some cases it can be zero. And so this is a p orbital, and very often from now on we'll color orbitals in different colors to represent their phases. And so when we have a p orbital, one lobe of the p orbital always has one phase, and the other lobe of the p orbital always has the opposite phase. And then there's a node. There's a region where the wave function is zero in between the two lobes, and this is right on the nucleus of the atom. And again, this is really important, so I put it in here again. Right, the sign of the wave function, or the phase, has nothing to do with electrical charges. It just tells us about the amplitude of the wave, whether the amplitude is positive or negative. It has nothing to do with electronic charges. Now, we also mentioned that the orbitals represent probabilities, right? So we're most likely to find the electron in these regions. And where there's a node, there is zero chance of finding an electron. So in fact, in a p orbital, if we imagine this plane that's going through the atom, there is zero chance of finding the electron in that nodal plane. Right? We're either going to find the electron in a p orbital above the plane or below that plane. Okay, so we talked about interference earlier, and this is where it comes back. In molecular orbital theory, a bond occurs when atomic orbitals overlap, and a bond occurs when they overlap constructively. So if we imagine these dots represent atoms that we want to bond, these wave functions are like the wave functions, if we were looking at them one-dimensionally, for, say, a 1s orbital in a hydrogen atom. And so in this picture, both of these 1s orbitals on each of the hydrogen atoms has the same phase. And so if we bring these atoms together, if we bring the waves or their orbitals together, they're going to line up constructively because they have the same phase. And so we're going to get constructive interference. And so we're going to get a higher amplitude in between the two nuclei. And so there's going to be a greater chance of finding the electrons in between the two nuclei. And so this is how we understand bonding in molecular orbital theory. It's the constructive overlap between atomic orbitals. Now, on the flip side, if we were to bring two 1s orbitals, say in two hydrogen atoms together when they're out of phase, we're going to get destructive interference. And we're going to get a node in between those two atoms. And where there's a node, the electrons can't be in. So, of course, this would be bad for bonding. If the electrons can't be between the two atoms, then we're not going to get a bond. We're going to get destructive interference. So to get a bond, we have to combine the orbitals, the atomic orbitals, in a constructive fashion. So this is a slightly different way of picturing what we just talked about on the last slide. So if I imagine bonding in an H2 molecule, so I have two hydrogen atoms, and these are their 1s orbitals. I've colored them the same color to represent that the orbitals are in the same phase. And so when I bring these two atoms together, they're going to overlap to form a new molecular orbital. That's the combination of the two atomic orbitals that I started with. And because the two orbitals had the same phase, they're going to interfere constructively. And so I'm going to get significant electron density in between the two hydrogen atoms, and that's what makes a bond when we're considering molecular orbital theory. And in fact, this is a sigma bond. The way we tell whether it's a sigma or pi bond, if you imagine looking down the internuclear axis, right, if we look straight down the H2 molecule, right, this molecular orbital, or this bonding molecular orbital, would look like a sphere. It would look like an s orbital, right? And so sigma is the Greek equivalent of the letter S, and so that's why we call this a sigma bond. It tells us about what is the symmetry of the orbital when we look down the internuclear axis. Now, it turns out one of the important things in molecular orbital theory is that the number of orbitals must be conserved. So if I'm starting with two atomic orbitals, I have to get two molecular orbitals. And so we've already seen how we can combine the two hydrogen 1s orbitals constructively to get a bonding molecular orbital where we have constructive interference. We also have to combine the molecular orbitals in a destructive way, where we get destructive interference, right? So now these have different phases, so they're going to destructively interfere, and we're going to get a node in between the two atoms. And so this is not conducive to bonding, and so we call this type of molecular orbital an antibonding molecular orbital. And so this is what happens in general. If we combine two atomic orbitals, we always get one bonding molecular orbital and one antibonding molecular orbital. Or if we combine 6 atomic orbitals, we're going to get 6 molecular orbitals. Generally, 3 of them are going to be bonding, and 3 of them are going to be antibonding. Okay, so what we're showing on this slide is a molecular orbital diagram for the H2 molecule. And it's showing how do the energies of the atomic orbitals change when they're combined to form molecular orbitals. So as we said before, right, we're starting with 2 atomic orbitals, a 1s orbital on one hydrogen atom and a 1s orbital on another hydrogen atom. And so I have to get 2 molecular orbitals. I get the bonding molecular orbital and the antibonding molecular orbital. And as is shown here, this is in general the case. The bonding orbitals are always lower in energy than the antibonding orbitals. And then these lines show us, these dashed lines are showing us which atomic orbitals are combining to mix to form the molecular orbitals. And the reason we do these in more complicated molecules, we might have more complicated ways of mixing the different numbers of orbitals from the atoms. Now, when we think about where the electrons are in the molecule, we fill up molecular orbitals just like we do atomic orbitals when we're doing electron configurations. So I started with 2 1s orbitals on the separated hydrogen atoms. When I bring them together to make an H2 molecule, I get these 2 new molecular orbitals, right? And each hydrogen atom is contributing 1 electron. And just like atomic orbitals, I can put 2 electrons in a molecular orbital. And they have to go in with opposite spins. And so the 2 electrons in the hydrogen atom both go into the bonding molecular orbital. And so the reason we form an H2 molecule is because it's energetically favorable, right? We can lower the energy of the system by forming this bonding molecular orbital and putting both electrons in that. The energy of the H2 molecule is lower than the energy of the 2 separated atoms. And so bonding in H2 is favorable. Just as a second example, if we consider the molecular orbital diagram for helium-2, now you may think, like helium-2, that doesn't make any sense. Helium is a noble gas. It shouldn't form helium-2. And you're absolutely correct in that. And in fact, molecular orbital theory explains why that doesn't happen. So helium has the same valence orbitals that a hydrogen atom has. All it has for valence orbitals is the 1s orbital. And so when we combine the 1s orbital on each of the helium atoms, we again form a bonding molecular orbital and an antibonding molecular orbital. Right, the bonding molecular orbital is lower in energy, the antibonding molecular orbital is higher in energy. But now each helium atom brings 2 electrons that we need to put into the molecular orbitals. And so we put the first 2 in the bonding molecular orbital. It's now full, so then we have to go to the antibonding molecular orbital and put those in. And so what happens when we try to form helium-2 is the energy that we gain from putting 2 electrons in the bonding molecular orbital is countered by the energy we lost by having to put 2 electrons in the higher energy antibonding molecular orbital. And so this is why helium-2 is not stable. And another way that we can think about this, in molecular orbital theory, we often talk about the bond order. And this is equivalent to whether something's a single bond or double bond, like we've talked about in Lewis theory and whenever we think about bonding up to this point. To calculate the bond order, you take the number of bonding electrons minus the number of antibonding electrons and divide that by 2. So in hydrogen, right, we have 2 bonding electrons, we have no antibonding electrons, so 2 divided by 2 is 1. We have a bond order of 1. Hydrogen has a single bond. In the case of helium, right, we have 2 bonding electrons minus 2 antibonding electrons. We end up with 0 divided by 2, so the bond order in helium-2 is 0, right? And so helium-2 does not form a bond. It is not a stable molecule. Now, so far, we've just been talking about the molecular orbitals that we can make by combining s orbitals. We can, of course, make molecular orbitals by combining p and d and f orbitals as well. Now, in organic chemistry, we're generally dealing with things that have s and p valence orbitals, and so we'll limit our discussion to that. So, p orbitals can also be combined to form sigma molecular orbitals. And we can either combine them such that they're out of phase, right? When I bring these two together, right, the blue is one phase, the red is the opposite phase. When I try to bring these guys together, those opposite phases are going to cancel each other out, and we're going to get a node in between. And so this is what an antibonding molecular orbital would look like. An antibonding sigma molecular orbital would look like when I combine two p orbitals. If I combine two p orbitals end to end, but so that the same phases are going to be pointing to each other, now because the blues are the same phase, they're going to overlap constructively, and I'm going to get a bonding molecular orbital. And again, the reason we know these are sigmas, if we imagine rotating it so that we looked just down the internuclear axis, if we looked straight down the internuclear axis, it would look like a circle or a sphere. And so that's why these are classified as sigma molecular orbitals. Now, we can also combine p orbitals to form pi molecular orbitals. So now we've rotated our atomic orbitals 90 degrees, right? So our atoms are here and here, or here and here. And if I combine them so that when I bring these two together, they're going to combine destructively, I get an antibonding molecular orbital. Or if I combine them so that the same phases are going to overlap, I can get a bonding pi molecular orbital. And if you notice, there's one node in the bonding pi molecular orbital, but there's two nodes in the antibonding pi molecular orbital. And this node is maybe the more significant one because this is in between the two nuclei, right? This is bad for bonding. So that's how we know it's an antibonding orbital. So this is just sort of all of the orbitals that we can make from a set of p orbitals. Right? A given atom, whether they're occupied or not, has 3 p orbitals in a given shell. So if we're thinking about something like carbon, whose valence orbitals are the 2s and the 2p's, each carbon has 3 2p orbitals. And so we can combine those to form 6 molecular orbitals from the p orbitals of the 2 carbon atoms. We can form, if we imagine like the px, the ones that are in the internuclear plane, those will form our sigma molecular orbitals, both one bonding and one antibonding. And then if the px orbitals are in the internuclear plane, then the pz and the py orbitals are perpendicular to the internuclear plane, and those will make our pi molecular orbitals, both 2 bonding and 2 antibonding. And the bonding pi orbitals are going to be degenerate. They're going to have the same energy, right? They're equivalent. They're just in different orientations. And the antibonding pi molecular orbitals will also be degenerate, right? They just have different orientations. They'll have the same energy. Okay, so if I ask you to draw how you would combine 2 s orbitals or 2 p orbitals to form a bonding or an antibonding molecular orbital, I would expect you to know how to be able to do that. I would not expect you to have to draw an NO diagram for something more complicated like N2, nitrogen 2, but I did want to show you what those look like. So this is the molecular orbital diagram for an N2 molecule. I haven't put in the electrons yet. Right, on the sides we put the atomic orbitals that we're combining, and then in the middle are the new molecular orbitals that we've created. And you can see that I've left off the 1s orbitals. Oftentimes when we draw MO diagrams, we just do it for the valence orbitals, and so we leave the core 1s orbitals out of our MO diagram, although we could include them if we wanted to. And so from each of the 2s orbitals on the 2 nitrogen atoms, we form a bonding and an antibonding sigma orbital. And from the 3 2p orbitals on each of the nitrogen atoms, that gives me 6 total atomic orbitals. We saw on the previous slide, we're going to get 6 molecular orbitals. we get 1 sigma bonding and 1 sigma antibonding, and we get 2 degenerate pi bonding and 2 degenerate pi antibonding molecular orbitals. Now, if we were going to put the electrons in, a nitrogen atom has 5 valence electrons. So we have in each atom, we have 5 valence electrons, so that makes a total of 10 valence electrons that we would add to our molecular orbital diagram. And so if we went ahead and put those in, right, I start with the sigma bonding molecular orbital. And so that's 2. Then I go to the next highest orbital. That's 4. Just like with atoms, when I have degenerate orbitals, everybody gets 1 electron before anybody gets 2. So I've given out 4. Here's 5, 6, 7, 8. And then the last 2 would go in 9 and 10. And just to show you where the bond order and how we can kind of connect molecular orbital theory to some of the other things we know from Lewis structures and other theories of chemical bonding that we've talked about, we know that the Lewis structure for N2 would look like that, and we would have said that N2 has a triple bond. Well, we come to the same conclusion from molecular orbital theory when we consider the bond order. So if you remember, the bond order is the number of electrons in bonding molecular orbitals. And so I have, in bonding molecular orbitals, I have 1, 2, 3, 4, 5, 6, 7, 8. And I subtract from that the number of electrons in anti-bonding molecular orbitals. And so I have 2 of those. Divide that by 2. 6 divided by 2 is 3. So molecular orbital theory tells me that the bond order in nitrogen is 3, right? And that matches our prediction from a more simple theory of chemical bonding from Lewis structures. It also tells me that nitrogen N2 has a triple bond. Okay, this is my last slide. And don't get too freaked out about this, but this is the molecular orbital diagram for water, for H2O. Now, certainly I'm not going to ask you to reproduce this, but I wanted to show it for a couple reasons. One, you can see, right, molecular orbital theory gets fairly complicated. We have fairly complex ways of combining the orbitals, the atomic orbitals on the oxygen atom and the hydrogen atoms to generate our molecular orbitals. But the reason I wanted to show these is to emphasize one of the important points about molecular orbital theory, and that is that molecular orbitals are delocalized. They're spread out over the whole atom. Right? This is one of the molecular orbitals in water, and we can see, right, this molecular orbital isn't between 1 hydrogen atom and 1 oxygen atom, right? It involves all the atoms in the molecule. And so this is why molecular orbital theory is particularly useful for talking about conjugated pi systems, where the electrons are delocalized. Some of our simpler theories of chemical bonding kind of break down when we try to go to those explanations. And so that's why we're introducing molecular orbital theory here, because it is very good at being able to describe delocalized systems, because in the molecular orbital theory description, electrons are fundamentally delocalized. The other thing that I wanted to point out is the higher in energy you go, the more nodes a molecular orbital will have. Or when you're comparing molecular orbitals, the more nodes they have, in general, the higher in energy they are. Right? So in this molecular orbital, we don't have any nodes. It's the lowest in energy. Right? As we go up in energy, we have 1 node, 1 node, 1 node. Now we've got, you can see a little purple here, it's kind of small, but now I've got sort of 2 nodes and 3 nodes and 4 nodes, and so the number of nodes increases as the energy increases for the molecular orbitals. And so what we'll do next is look at how do we use molecular orbital theory to explain some of the properties, or how do we apply it to these conjugated pi systems that we've started looking at.